Hello, everyone, and welcome to Calculus. Today, we're going to be studying the definite integral and its relationship to the area under curves. So last class, we did area under curves using MRAM and RRAM and LRAM. So when you're given a graph of some kind, you could sit there and make it into a whole bunch of little rectangles. Not doing these in any particular way, just trying to give you the concept of it. All these rectangles are going to be a length times a width. The length of them is going to be the same as f of x, which is its height. And the width of them is going to be x, but delta x, meaning the little bit of change of x you make each time, delta x. If you add up all those rectangles, you'll get the area. So this really complicated looking notation is just that. Sum, this notation, the sigma, means sum, which means to add up. So you're adding up all of the f of x's times delta x. So this is just length times width, and this is adding them up. So it's a complicated looking definition, but it's really not that bad. I will read it out loud. Let f be continuous on a to b, and let AB be partitioned into n subintervals of equal length. So if you're going from A to B, that entire distance is B minus A, and then you're going to divide it up into some number of rectangles. So we'll call that n. That represents each little width. That's where this formula comes from. So delta x is B minus A over n. Then the definite integral of f over a minus b is given by the limit as n goes to infinity. That means instead of just doing 4 intervals like we did yesterday or 5 intervals, what if you did an infinite number of intervals? You made so many little teeny tiny rectangles. The teeny tinier they are, the more perfect the measurement. If you're trying to find area, if you make a big rectangle, look at all that overestimation you're going to get. But if you make triangles that are literally, not triangles, rectangles that are literally so small that you can't even see them go over and under, they literally are just f of x, then you're going to get the perfect area. How would you do that? If you made n go to infinity, if you just had a million of them. So we're going to take this definition that was already kind of complicated, and we're going to add the limit as n approaches infinity. So in English now, if you make an infinite number of rectangles in the space under a curve and add them up, the answer will be the same as if you calculate the definite integral. So when we were doing that the other day, and we were doing the integral or the area from -1 to 3, I think we did, of x squared plus 1. We used MRAM and RRAM and LRAM, but instead you can do the integral from -1 to 3 of x squared plus 1, and it'll give you the exact area. Because integral means sum. It's an S. It's the equivalent almost of this sigma that you've already learned. And all these upper and lower numbers are telling you is where you start and where you end. And then this is the f of x. So what's missing? The width. And that's where the dx comes from. That's why we always write f of x dx. This is length times width. And if you add them all up, infinite number of them, that's what an integral is. All right, so big concept. We're going to do just one little problem with this notation in the honors class, but in the AP class, just so you know, we'll be having an entire worksheet on making these transformations because they do get a little bit more complicated. But in the simplest form, the interval -1 to 3 is partitioned into n subintervals of equal length. Delta x is equal to 4. That 4 came from the fact that you were at -1, you went to 3, that's 4 spaces, divided by n. Let m sub k denote the midpoint of the k subinterval. Express this limit as n goes to infinity. As soon as you see n goes to infinity, it's going to be an integral. So these two pieces make that integral. And how do you do the length each time? The length is just the height of whatever the function is. And then delta x, or dx. In this particular case, integral of 3x squared minus 2x plus 5. Because that's what you would keep changing each time, but we're just going to call it x, from -1 to 3. Pretty cool, right? They do get a lot harder than that, but in its most basic format, if you're taking some kind of business calc next year, you probably don't need anything more than that, so I'm going to stop there for now. But like I said, in AP, we will do some much more complicated ones than that. All right, so there is one catch. In order for this to be true, in order for area to equal integral, it only means net area. In other words, this only works if your area is above the x-axis. As soon as you go below the x-axis, it doesn't work anymore because this area is going to be negative. So we're going to have to deal with that. All right, formal definition. If y is equal to f of x is non-negative, so again, that means it's above the curve, and integrable, so I'm able to take the able to integrate, over a closed interval from a to b, then the area under the curve, y is equal to f of x, from a to b is the integral. So just like back when we were doing derivatives, I really wanted you to memorize derivative is slope. Slope is derivative. Now I want you to think area equals integral. That's what an integral does. It tells you the area underneath the curve. But in your little head, you might want to memorize that it actually means net area equals integral. So the integral is the net area between the curve and the x-axis. Parts of the area above the curve are positive, and parts of the area below the curve are negative. I'll give you an example just so you can see what I'm trying to say. So if we do this integral, very straightforward. Again, I always say the derivative of cosine is, negative sign, so I need a negative there. I put on my limits. It always goes top minus bottom, so 5 pi halves minus negative cosine of 0. Cosine of 5 pi halves is 0, and cosine of 0 is 1. So my answer is 1. So let's compare that to area. I'm going to draw the sine curve. Sine goes up, and then down, and then up, and then down. It does this in the other direction too. So this right here is pi halves. It comes back down at pi. At 3 pi halves, it's down there at -1. And this is 2 pi. So this right here is going to be my 5 pi halves. So I want this area and this area and then this area. So think about that for a minute. Compare my answer to the area between the curve and the x-axis. So area means integral. If area means integral, are you telling me that this entire pink area is equal to 1? Of course it's not, because this is a positive area and this is a negative area. So they've canceled each other out. This must be equal to 1 because that's all that's left. So if this half an arch is 1, this arch must be 2, which means this one must be -2. So if you're asked to find the total, not net this time, the total area, it would be 5. You have to think of this as an area. Just because it's underneath the x-axis doesn't mean you can't make it positive. I want to know this area and this area is in this area. Mathematically, it's a negative number. Just like velocity. Velocity has a sign associated with it. When somebody says negative 30, that either means it's going down or backwards. But with speed, we don't ever use negative. No one says, I went to Flemington at 50 miles an hour and I came home at negative 50 because I was going in the opposite direction. You just know to take the absolute value and just call it 50. Well, when you're trying to find area, you want the absolute value of all the sections. But integral is always going to give you net area. And that's why the integral is only equal to 1. So you might be thinking, is this really helpful then? You might think it's not helpful because if you can't get the area from the integral, then how is it helpful to you? You just have to do it in 3 sections. You have to sit there and find this integral, and then this one, and when it comes out negative, you make it positive, and then this one. So you will have to be good at graphing. We're going to do a lot of it. All right, what I want you to do is I want you to make a line down the little part of your paper there, and I want you to label this side net, because this is going to give me the net always. The integral always gives you net. But if I want to find the total area between the curve and the x-axis, total area between the curve and the x-axis, that's what's going to go in this column. So in other words, I want the total area between pi and 2 pi. Okay? So based on what we learned from this one, in order not to actually do all these integrals, we're just going to keep using this concept that in sine, one curve is equal to an area of 2. We're going to use that for all of these so that we don't have to, so we can move quickly and not do all the math. So total area, they want to know this space right here between pi and 2 pi. What is that area? Negative and positive don't matter. This area is 2. But if you actually did this integral, what would you get? Negative 2. Hopefully this is making some sense for the difference. If it's not, that's why there's 10 of them. We're going to do a whole bunch here. Total area always has to be drawn. An integral doesn't need a drawing. You can just do the math. Okay? But a total area needs a drawing. So I'm going to go from 0 to 2 pi. What is that integral? If you did this integral out, what would you get? You're going to get 0, because this integral is calculating the net area and gave this a positive 2 and this a negative 2, and it came out to be 0. If you don't believe me, of course, you can actually do the integral from 0 to 2 pi, negative cosine of 2 pi minus negative cosine of 0. Cosine of 2 pi is 1, and then this is plus 1 is 0. But if you understand the graph, you can just look at the graph and say, oh, it's going to come out to be 0. But what is the total area? Not 0. It's 4, because this is 2 and that's 2. Let's do another one. I'm going to continue my line here. This is net, and this is total. So now I'm going from, I just keep using sine because I'm just trying to give you the concept of it. We're not really trying to practice different integrals. We're just trying to practice what net versus total means. So now I'm just going to pi halves. I'm stopping there. Now, given that a whole arch has an area of 2, this little half arch must have an area of 1. If I were to actually do this integral, what would I get? I would also get 1. These two answers will come out the same if you're above the x-axis. Net and total only differ if there's some parts that are negative. All right, this next one is an exercise in graphing. What does that plus 2 do to it? it does move it up 2. So now, if you want, you can draw a little line there and think of that as your center. So now I want the area from 0 to pi, which is normally right there, right? But now it's 2 higher than 0. It's normally right at 0. That's why I drew that line for you. But now it's 2 higher. So can you find, oops, this area? You don't have to be able to find that area. You can use the integral, because if it's above the x-axis, then the integral will give you the correct answer. So this is going to be 2x minus cosine of x from 0 to pi. That is 2 pi minus cosine of pi minus 2 times 0 minus cosine of 0. So cosine of 0 is 1. So this becomes positive 1. Cosine of pi is negative 1. This becomes 1 and 2 pi. So the final answer is 2 pi plus 2. How could you have done that graphically? Well, we know that this little region has an area of 2. And since this is a rectangle, I can do length times width, which is 2 times pi. Add them together, and I get 2 plus 2 pi. Some people are going to do it graphically, and some people are going to do it algebraically. It doesn't matter to me. What matters is that you can make the graph and then say, okay, it's all above the x-axis, so the integral is going to work. If it goes below the x-axis, the integral won't work. If you're thinking, I'm not sure I'm going to be able to graph these. If you're in honors, you always have your graphing calculator. You don't actually have to know how to graph them. But I'm going to keep teaching you because I want you to learn. So how does this 2 affect it? This 2 is going to make it twice as tall. So 0 times 2 is still 0. But 1 times 2 is going to bring it all the way up to 2. And then times 2 is still 0. Times, normally now we would go down to negative 1, but times 2 is negative 2. And then back to 0. So it's twice as tall. We're only going from 0 to pi. Is that section above the x-axis? It is. So somebody that's doing it graphically might be saying, oh, I bet it's 4. It's twice as big. So it's normally 2. I bet it's 4. How can you check that easily? You don't have to actually redo this integral. You can take the 2 out. How does the 2 affect it? Sure enough, it's 2 times the area under sine. So it is 2 times 2 is 4. So obviously these 3 in a row here are meant to show you the different effects on the graph. Here's the parent graph. Here's the one that moves it up 2. This one is making it twice as big. And then this one is going to move it to the right 2. That's not working. To the right 2. So go ahead and make a graph of that while I do it on my little board here. Ooh, this is going to be hard, because what is this axis counting in? It's counting in pi. So if it's counting in pi, how do I add 2? It's not as easy as this one when we moved it up 2, and it was at 0, and this is counting by ones. So again, your job is to figure out whether or not the graph is affects the area. So I'm going to show you something very cool. Notice that the limits of integration changed. I can't move this right. It's just not working for me. So I'm going to make a u substitution. U is x minus 2. And then my new integral, which by the way, du is just dx, so it didn't affect anything. So I'm going to call this sine of u du. And now when x is 2, what is u? 0. Because 0 or 2 minus 2 is 0. And what about when what is u when x is pi plus 2? So when x is pi plus 2, u is pi. All right, so we just did changing the limits of integration the other day, and this is another excellent use for it. If you change the limits of integration, now I've made a graph that I do know. Oh, it's just a sine graph, and I'm just going from 0 to pi. The answer is definitely 2. Number 9. Now I'm going from negative pi to pi. I'm just going to continue my line here. Net total. So whenever you want to do a total area, you always need the graph. This time I'm going to go from negative pi to pi. What is this going to be? Total area is going to be 2 plus 2. So the total area is 4. The net, if I actually just did the integral though, because this is actually negative and this is positive, this integral is going to come out to be 0. Number 10, x over 2. So this one changes its period. So I don't know if you remember this, but this is really sine of 1/2 x. So this is your b. And you may recall that the period is calculated by doing 2 pi over b. So in this case, 2 pi over 1/2, which is 4 pi. Like, oh man, I don't remember that at all from trig. Yeah, I had a bad feeling about that. So here's 2 pi. I need to get all the way over to 1, 2, 3, 4 pi. So this is going to go from 0 up to 1. And at 2 pi, it's finally coming down. So it takes an entire 4 pi. Because it's moving half as fast. So that half means it's only traveling half as fast, and that's why its whole period is 4 pi. So to go from 0 to 2 pi is just this. But is that still going to be equal to 2? One arch was 2 when it was just, oh, I guess we can look up here. One arch was 2 when it was just going from 0 to pi. Is it still this way? Well, the good news is that to get the total area, you can actually do the integral. So I'm going to do my integral. U is equal to 1/2 x. Du is equal to 1/2 dx. And then, so I need to add a 1/2, which means I need to add a 2. So now I have 2 integral of sine of u du. I can actually do the integral, or I can just change the limits of it. So when x is equal to 0, u is equal to 0. When x is equal to 2 pi, 1/2 times 2 pi comes out to be pi. Look at that. You already know the answer of sine of u from 0 to pi. It's 2, but that times that 2 makes it 4. So the actual integral answer is 4, and the total area is 4. Why are they the same? Because you did not go below the x-axis. All right, if you want to try one on your own, a whole new one, see if you can do cosine. You know I'm going to do it for you, but just thought you might want to try it. So cosine starts at 1. At pi halves, it's 0. At pi, it's -1. 3 pi halves, it's 0. And then at 2 pi, it's back up to 1. So cosine looks like this. And it keeps going. So what does it do from 0 to pi? Its arches are the same size, but this is going to come out to be 0 without doing any work at all. Well, I mean, I guess I graphed, that was my work, but without doing any algebra. But what is its total area? Its total area is 1 plus 1 is 2. Okay. So that was a lot of problems to try and just get you to understand the difference between net area and total area. I hope it helped. All right, some thinking questions now. Suppose k is any positive number. Make a conjecture about the integral from negative k to k of sine of x dx. Support my conjecture is going to be my graph. So sine looks like this. I know you're sick of sine. We've done a lot of sine today. No matter where I go, I can go here and call that k, and then this would be negative k. That definitely equals 0. Can I make that true if I put k in a different spot? Absolutely. Go back. We'll do a couple more backs. Won't do any more backs. Gave up on me. I pushed it too far. All right, so I'm just going to draw a new one. So let's say I go way over here. So that same distance would be way over here. Then this one still cancels this one, and this bit over here, I guess into the exact same spot, would go to that over there. So it's still 0 no matter what you do. What would be a shortcut for calculating the total area between the x-axis and sine of x on that interval? So what's nice is that when you have to go from negative k to k for sine of x, you could just go from 0 to k, which is always lovely to plug in a 0, and then you don't have to plug in a negative number and just multiply your answer by 2. Because if you go from 0 to k, you're going to have the same thing on the other side. So this is a great shortcut that people like to use. Does it work for every function? No, definitely not. So be careful that you could have a parabola, which you might be thinking, oh, parabolas are even. Not all parabolas are even. So this parabola is not even. If you went from k to negative k, right, the area would not, you can't just double it. So it doesn't work for everything. It only works for odd or even functions. So, for example, an odd function, see how you could double that area? And then an even function, you could just go from 0 to k and also double that one. Number 14, evaluate the integral from negative 2 to 2 of the square root of 4 minus x squared dx. So we haven't done one of these yet today. Use substitution. U is equal to 4 minus x squared. Du is equal to negative 2x dx. I'm going to change this to a 1/2. I don't need the parentheses because I'm changing it to a u also. U to the 1/2. And I don't have the 2. And I don't have the x. You can't add an x to a problem. It's not allowed. You can add a number, a constant, but you can't add the x. So this isn't going to work. This is why I need you to understand that integral means area, because you are definitely going to get a problem where if you can't do the integral, use area. If you can't do the integral, use area. So let's graph that. You might be looking at it thinking, I don't know what that looks like. You do. You just don't know it yet. Square both sides. Add x squared to both sides. See it yet? It's a circle. It's only the top half of the circle, because if we were to go backwards, if we started with a circle and then put the 4 on the x squared on the other side, and then took the square root, we would normally have plus or minus. They've only given us the plus, so it's just the top half of the circle with a radius of 2. What is the area of a circle? The area of a circle is pi r squared. So for this circle, it's pi 4, not 4 squared. I already squared it in my head. Pi 2 squared, which is 4 pi. But remember, we only want the top half of the circle. So this integral from -2 to 2 is equal to 2 pi without doing any actual integration, because we tried to do the integration and we couldn't. So if you can't do the integral, use area as a backup. Of course, that would require you knowing how to graph. So I've been trying to preach graphing since I met you in either Algebra 2 or in pre-calculus. This is why. It wasn't just to be mean. And of course, this also works for constant functions, just going way back to the concept of the train, where it was going at a steady rate of 75. So just y is equal to 75 from 7 to 9. The area under the curve is still the integral. We didn't do it this way before, but if you integrate that with respect to x, you get 75x from, 7 to 9, which is 75 times 9 minus 75 times 7, which comes out to 150. Integral means area. Okay, so you can do this numerically on your calculator. You just need to use your Math 9 button and type those in. I'm actually just going to give you the answer to the first one, which is 2.043. And I am going to look for the other two when I check your notes. Otherwise, you'll just write down the three answers. I just need to know that you can correctly type that into your calculator. Okay, last page. So the theorem about integration states that all continuous functions can be integrated, are integrable. Actually, though, some discontinuous functions are integrable also. Think about this. When you guys did in modeling and optimization, you had the barn, and then you built a fence where one side of the barn served as part of the fence. Sometimes people get confused. It changes perimeter. Perimeter is just 2x plus 1y because you don't need any fencing along the barn. But area doesn't change. Even though you aren't using the fence, area is still x times y. And sometimes people try to change that, but missing a little piece doesn't change the area. If he decides to leave a big open gate, nothing there, not even a barn wall, doesn't change the area. Okay? So we're going to make a graph of these and show you that it doesn't change the area. Allow me to plug in my computer. See, don't you feel like we're in school, having to stop and plug in my computer? All right, so what does this graph look like? So if x is positive, then the absolute value doesn't matter. So x divided by x is just 1, whether it's 1 over 1, 2 over 2, 3 over 3. So it looks like this. But if x is negative, then it would make it positive. So if x was, say, -2, the absolute value of -2 is 2, but divided by -2 would give you -1. So this graph looks like this. This is not continuous. It doesn't have a derivative here, but you can do the integral. How would you do the integral from -1 to 2? Integral means area, even if it's a discontinuous function. So this area right here and this area right here. This area is 1 by 2, and this area is 1 by 1. But what do you think I want for the answer here? 3 or 1? Does this count as -1 or does it count as +1? Well, because I'm doing an integral, integral means net area. So the integral is 1. If I were asking you for what is the total area between the curve square root of x over x and the x-axis, then you would have said 3. You only need to do that if it says find the area. But if you're just doing an integral, then you can just go ahead and use net. So here's another one that we've done a lot in the past. This factors. So even though it looks like it was going to be some horrible thing with oblique asymptotes and who knows what else going on, because you see the power is higher in the numerator, it's not. All you have to do is factor it, and this is actually just x plus 2. But you may remember when we studied this in pre-calculus, it has a hole in it. So it looks like this, but you can't have x be equal to 2. So at 2, there's a hole. Well, as I'm going from 0 to 3, does that hole affect my area? It definitely does not. The hole has no effect on the area. So you can just go ahead and do the integral of x plus 2. You still don't want to do the integral of this, right? You can still use the simplified version. So I'm going to do the integral of x plus 2 from 0 to 3, knowing that the whole doesn't matter. I get x squared over 2 plus 2x from 0 to 3, which is 9 halves plus 6 minus 0 plus 0. So 9 halves is 4.5 plus 6. The answer is 10.5. Okay. Number 3. This is the greatest integer function. We also learned it as a bracket with an x, and even some books, a double bracket with an x. Unfortunately, the world has not been able to agree on this one. Definitely not continuous. Definitely one that we've never studied that integral. You've learned all your integrals. Trig functions, exponential functions, logarithmic functions, but we never did greatest integer function. That's because you don't need it. Integral means area. So I always make this step first. 2, 3, 4, 5. And then 1, 2, 3, 4. I need to get up to 5. So I'm going to make my steps. This is really just review. I'm sure you've already got the concept that integral means area. So there's no area underneath this one, but it's going to be this area plus this area. Do the open circles matter? They do not. And then this area, and then this area. So if you're ever given a greatest integer function, and you're like, we didn't learn that. I know. I didn't teach it to you. Because integral means area. So this is a 1 by 1 box, a 1 by 2 box, a 1 by 3 box, a 1 by 4 box, and together they make 7, 8, 9, 10. 2 more. Thanks for hanging in there with me. This one is on here because people struggle with, again, like I said, this is just my opportunity to do some review algebra with you because people struggle with this. I definitely would factor out the negative and rewrite it in the form that you're used to. If I redistribute that, negative x squared and then positive 9, but isn't it so much nicer now? So negative x plus 3, x minus 3. So this is just negative, because these cancel, x plus 3. Or you could do the integral of negative x minus 3. Graphically, what does this look like? This is a line now, negative x minus 3. So it looks like that. And it has a hole at 3 because you can't actually let it be 3. As I go from negative 5, this is far, 1, 2, 3, 4, 5, all the way to 6, 1, 2, 3, 4, 5, 6. Does that hole matter in my area? It absolutely does not. So you have 2 choices. You can do the integral or you can use the area. The answer either way had better come out to be negative. You can see there's a lot more negative space than there is positive space. So if you're using integration, then you would say negative x squared over 2 minus 3x from negative 5 to 6. Not the easiest math in the world. Negative 5 squared is 25. Sorry, we do the 6 first. Negative 36 over 2 is negative 18 minus 18. And then negative 5 squared is 25. So negative 25 halves plus 15. I don't know. This isn't looking very pretty, right? So you could do it by area. This is 6 plus 3. This is a 9 by, and how far down does it go? So somebody might not want to do that. But at 6, if you plug a 6 in here, it's negative 9. It's not that bad. So 9 times 9 is 81, but it's a triangle, so base times height divided by 2. 81 over 2, which is 40.5. Not terrible. And then this little triangle, where is it when you're at 1, 2, 3, 4, 5? When you're at 5, if I plug negative 5 in here, negative 5, I'm up at 2. So this is a 2 by 2. 2 times 2 is 4, divided by 2 is 2. Lots of 2's. But this is negative, and the 2 is positive, and that gives me negative 38.5. Was that easier? I don't know. If I had done this out, I also would have gotten negative 38.5, but I probably would have pulled out my calculator for it. Okay, one more greatest integer function, but it has been moved. Just going to erase this real quick, or white it out so I can fit everything. There we go. So it's a really big greatest integer function. So it's also been moved. Oh, it's twice as big. All right, here's something really interesting. I do not feel like graphing that twice as big, and I certainly don't feel like moving my greatest integer function over. I'm really good at graphing it right on the axis, right on the origin. So I'm going to use u substitution. I'm going to take out the 2 and just ignore that. That's a constant. I can take my answer and multiply by 2. But I'm going to let u be x minus 3. Du is just dx, so it doesn't affect anything. Greatest integer of u. And if u is equal to 5, 5 minus 3 is 2. If u is negative 6, then negative 6 minus 3 is negative 9. So I need to get from negative 9 to 2. But this is still huge, right? 1, 2, 3. I don't feel like doing that. But do you think that you could figure out the pattern after just a few of these? I think that you can. So I'm only going to go up to 2, which is right here. So there's nothing here. This one is 1. This one is 1. This area is 2. This area is 3. Do you see where I'm going with that? So in order to get negative 1, negative 2, negative 3, if I go all the way to negative 4, I'm going to have to add a 4 in there. So if I go all the way to negative 9, I must have to add a 9 there. So let's add those up. 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. Remember that these are all going to be the negative ones. Plus 0, that's right here. It doesn't have any area under the curve, plus 1. So these are actually all negative because they're underneath. And as just a little shortcut for adding them up, I mean, you can get out your calculator if you want to, but 10, 20, 30, 45. So negative 45 plus 0 plus 1 is negative 44. So doing the greatest integer function from negative 9 to 2 is negative 44. I have to double my answer, and I get negative 88. There is no algebraic way to do this one. You have to do it by graphing. There's no formula for integral of a greatest integer function. All right, that concludes our lesson on definite integrals as they relate to area under a curve. Have a great day.